Okay, so this is the lesson video for 8.4 over types of quadrilaterals and parallelograms. First, we are going to start out with your bell work question. So go ahead, pause the video, and find the area and perimeter of this figure. Okay, so for the perimeter of this triangle, you are going to add up all the side lengths. You have 9.5, 8.5, and 10. So that gives you a total of 28 feet. And I did tell you in the instructions the unit was feet. And then for the area, you would do the base times the height divided by 2. So that would be 10 times 7 divided by 2. You'd multiply 10 times 7 to get 70 divided by 2. And then you would reduce that to 35 feet squared. Okay, so remember, your units for perimeter are just the typical unit, the first power, and then the unit for area is the unit squared. So we are going to be working on this section of notes. It's 8.4. We have already talked about polygons in general, and we've talked about triangles, which are three-sided polygons. So today we're going to be focusing on quadrilaterals, four-sided polygons, and a specific type of those, which are called parallelograms. So the objective for today is I can identify parallelograms and use basic properties of parallelograms. So we're actually going to start out with a definition that is something you'd probably figure out, but again, I just want to make sure that this is crystal clear, and that definition is diagonal. Again, most people know this word in a general sense, but maybe not mathematically. And a diagonal mathematically is a segment that connects two non-consecutive vertices. A segment that connects two non-consecutive vertices. And so as we talk about parallelograms and we talk about their diagonals specifically, we will go over that more. But technically that's not a vocab word I believe you've seen this year, so I wanted to make sure you'd seen it. So let's talk about what a parallelogram is. Generally, a parallelogram is a quadrilateral in which both pairs of opposite sides are parallel. And so as we go through and we further define parallelogram, let's go ahead and label our picture. We do know how to label parallel sides. Sides that are parallel to each other get the same number of triangles. So because I put one triangle on the left side and right side of that figure, that tells me that those are parallel to each other. And then the other sides are parallel to one another as well, so they're both going to get two triangles. Again, the number of triangles tells you which sides are parallel to each other. So we do have to have different numbers of triangles on this figure because the sides on the left and the right are not parallel to the sides on the top and the bottom. The opposite sides are the ones that are parallel to each other. They're not all parallel to each other, or we wouldn't have a polygon. And then we do have some properties, and again, as we go, we're going to continue labeling the picture. So the first property of parallelograms is that opposite sides are congruent. And again, we've talked about congruence a lot this year, so when you have a parallelogram, sides that are opposite each other are congruent to one another. The way we show that is with tick marks. So again, the number of tick marks tells you what goes together. So since I put a tick mark on the top and the bottom of that figure, those opposite sides are congruent. We can do the same thing on the left and the right side, but they might not be congruent to the top and the bottom. So we use a different number of tick marks. The next thing that we know about parallelograms, or we will know in 1 second, is that opposite angles are congruent. I guess I'll just use the congruence symbol. And again, we do have a way of denoting this. So the way we show that angles are congruent are with the same number of arcs. So I put one arc in the upper right and one arc in the bottom left corners. And then I can do 2 in the other 2 corners to show that those are congruent to one another. Then consecutive angles, and this is something we struggled with in our parallel lines unit, so I'll talk about consecutive angles a bit, but consecutive angles are supplementary, meaning they add to 180. So if that's something that you forgot, make a mental note. Consecutive angles are angles that are next to each other. And I will say on your homework assignment, you have plenty of consecutive angles. you need to make sure that you are adding two consecutive angles together to give you 180 degrees. And it can't, you can have, you can have those two consecutive angles on the left. These two top angles would be consecutive. These two angles on the right would be consecutive. It just has to be angles that are next to each other. Okay, they're kind of in the same side of the parallelogram, then they would be considered consecutive as opposed to opposite. And then the last thing, and I'm actually going to change colors just to see this a little bit easier, is that diagonals bisect each other. I think sometimes people think bisect just means like runs into or intersects, but bisect has a kind of a more special definition than that, and that it means they cut each other exactly in half. So as I go through and draw in diagonals, and sorry, that one wasn't going very good. Let's draw a better one. Here we go. Okay, so these are the diagonals of this figure. We are connecting the non-consecutive vertices of the figure, so the corners that are not, directly next to each other. If I were to label this diagram, not only do those diagonals run into each other, and they definitely do, but additionally, they bisect each other. So that means one half of the diagonal is exactly congruent to the other half. And same thing going the other direction, they might be different measurements though. So going the other direction, one half is exactly congruent to the other half. So everything we're doing today essentially is based off of these properties. These are properties you want to memorize. You really want to ingrain them in your brain because we're talking about parallels. A lot of the rest of this unit, parallelograms, the rest of this unit, and these are the properties that we're going to continue coming back to. So let's do some examples relating to these properties. And as we go through this whole unit, please look up toward the properties and see if you can figure out how the properties relate to the question. So for A and B, it says find the value of each variable in the parallelogram. Also, state the property that you used to find it. So as I go through and I look, I notice a couple things going on. First off, on the first example, I have side lengths. Let me pick a better color. I have side lengths given to me. Okay, I'm told that the left side of that parallelogram is 4y minus 3. And then the opposite side to that is 3y plus 1. Well, one of the properties that we just learned, and it's a property we're going to use a lot, is the fact that opposite sides are congruent in parallelograms. So what I can do, since they're opposite sides, they have to be congruent. I can set those two equations equal to each other and solve. So I'd get 4y minus 3 equals 3y plus 1. I can then move all my variables to one side, so I would subtract 3y from both sides, get y minus 3 equals 1, and then add 3 to both sides to get that y equals 4. We also happen to know about the other sides as well, so as I look at this figure again, I'm also told about the other sides. The top side of the figure is 4x plus 6, so that has to be congruent to the bottom side of the figure, which is 7x minus 3. Once again, since they are opposite sides on parallelograms and they have to be congruent, we can set their expressions equal to each other, get everything to one side of the equation. So I'll subtract 4x. 6 equals 3x minus 3. Move all my constants to the other side. 9 equals 3x, and then divide both sides by 3 to get that x equals 3. Now, I could certainly ask you to plug those back in and figure out what the actual side lengths are, and you can do that if you would like to, but for the purposes of this presentation, I'm not too worried about that. All right, example B. There is one thing that is different in example B versus example A, and that's that you are not always given side lengths. In example B, you're actually also given angle measures. So as I look, and let me highlight those a little bit differently, that might be easier. As I look in this figure, not only do I have some side lengths, which I do, that's true, I have the left and the right side measurements, and I will deal with that in a second. But I also have those angle measurements. And so when we're talking about the properties being used on this problem, I have to say both opposite sides and angles are congruent. So for the angles, once again, we can set those two measurements equal to each other and solve. I'll just add 21 to both sides to figure out what D is equal to. D equals 126 degrees. Or honestly, you don't even need the degrees for that. It's just a variable. And then again, I can do the same idea with the side lengths. So Z minus 8 equals 20. Add 8 to both sides to get that Z equals 28. So again, just using those properties and applying those properties. Now here is the angle relationship that you're going to make mistakes on. Something similar to example C, and you will see you have problems on your homework that are similar to example C, but you are setting up with expressions, so they're even more complicated. The general idea is that you have to remember how consecutive angles are related to one another. And so when I'm going through on this problem, I am told, and maybe it's not what we'd expect, we'd probably be asked to find angle C, but we're told to find angle B. Well, here's what you have to remember. Two angles that are consecutive have their own special relationship in parallelograms. Okay? Consecutive angles are supplementary. So any angles that are in that position, they're next to each other in a parallelogram, but they are not across from each other. Those angles cannot be set equal and solved. They have to be added together for a sum of 180. So all I would need to say is that 51 plus the measure of angle B equals 180. Then I can solve for the measure of angle B. Subtract 51 from both sides. The measure of angle B equals, and I get 129 degrees. Now, I do want to make a separate note. On your homework, there are examples very similar to this, but instead, you might be told that this other angle is 2x. You might be told that other angle is 2x minus 9, something like that, okay? If you were to see something like that on your homework, remember that you add together the measurements and set them equal to 180, creating a problem that you can solve using your operations to solve equations. Okay, so really check again on the first sheet of the written homework. There are plenty of problems that have consecutive angles versus opposite angles. A lot of you are going to get in the habit to set whatever's written on the page equal to each other and solve, when in reality, anytime you have consecutive angles, those have that supplemental relationship, and so that is important. All right, why don't you take a second, so pause your computer and try to do example D on your own. So we're told that we have a polygon L, M, and Q, and we are trying to find all of these features. All you need to do is tell me the value of the feature and the reason that that feature has that value. Okay, so hopefully you've already completed this and are just checking it with me. The value of LM is 13, and if you look at the figure, we know that because it is a cross or opposite of another side length that is 13, and so our reason is that opposite sides are congruent. So if the opposite side to LM is 13, then LM is also 13. LP is 7. The reason for that is the other half of the diagonal was 7, and those are going to match because diagonals bisect each other in parallelograms. LQ has a value of 8. Again, across or opposite sides have the same measurement. So across from LQ is 8, therefore LQ is 8 because opposite sides are congruent. And then we're going to start talking about angles. So angle MNQ. MNQ is this entire angle here, and it is opposite of a 100-degree angle. So MNQ is 100 degrees because opposite angles are congruent. And then this is the hardest one. We are told to find the measurement of LMQ. It is actually not the full measurement. It is only between LM and that diagonal. And this one's actually a bit tricky. You have to remember that we have parallel lines. And so LMQ is actually 29 degrees because these are parallel lines cut by a transversal. So we're actually going all the way back to when we were doing proofs and we were doing parallel lines cut by a transversal. For the reason on this, it's alternate interior angles theorem. Because again, the idea is that alternate interior angles are equal to one another. Now, we have not done any problems using what we know about diagonals. So let's go back to the properties of parallelograms for a second and remember that diagonals bisect each other. So we've talked about that a little bit, but we have not set up any equations using this property. Is it any harder? No, it is not harder than the other examples we have tried. So it just says find the value of each variable in the parallelogram. Also state the property that you use to find it. So again, we know based off how parallelograms work that opposite sides are congruent, opposite angles are congruent, diagonals bisect each other, and consecutive angles are supplementary. So in this example, I have some information about diagonals. Again, we know that two sides of each diagonal are congruent. So one thing I can do is I can set 2u plus 2 equal to 5u minus 10. The reason I can do that is they're two halves of the same diagonal that's been bisected, so they have to be equal to each other. And then the other thing we would have to solve, and I'll set it up separately, is that 6 would equal v over 3. Now, don't question the second example. A lot of people see that v over 3 and freak out. It's dividing that v by 3, so the way we get rid of it is with multiplication of 3. So v equals 18 as my v value. And then the first equation, you get all the variables to one side. We move all the constants to the other side. So 3u equals 12, and then we divide both sides by 3 to get that u equals 4. Guess I'll just double underline. All right, now the last thing that we are going to be talking about today is proving if you have a parallelogram on a coordinate. And I'm going to be honest with you guys, I like the first example. The second example is not as good, and I'll tell you why in a bit. But what we're going to be doing is we're going to try to figure out, looking at this parallelogram, it seems like it's a parallelogram, but we're not entirely sure. How can we prove it mathematically? And the way that we're going to do this comes back to what the definition of parallelogram means. So a parallelogram, by definition, says that it's a quadrilateral where both sides, or opposite sides, are parallel to each other. So what we need to test and have some mathematical way of proving is that LM is in fact parallel to KJ, and that KL is parallel to JM. So that's our entire purpose in this problem. What's nice about this is actually in past classes, probably in 7th or 8th grade, we talked about, well, whoever your math teacher is, I guess that's the collective we, talked about slope and how that's related to parallel lines. And the way that parallel lines work, and I'll write this at the bottom, is parallel lines have the same slope. Okay, it is how you guarantee that you have parallel lines. If two lines have the exact same slope, they're going to be parallel. They will never run into each other. So what we want to do is we want to look at each of these sides individually, and we want to say, what is the slope of that segment? And if all of those slopes are compatible with each other and the opposite sides have the same slope, then we should be good to go. Here's how I do slope, especially in this circumstance. First, I look at it and I say, okay, is that positive or negative? And you should be able to look at that line segment LM that I've highlighted and just tell me if it's positive or negative. If that's something you cannot do, that's something I want you to work on. So that particular line goes down as it goes to the right. It's kind of tipped over to the right. So that actually has a negative slope. And then all you have to worry about is the rise and run. So I'm literally going to focus on the rise now. I'm going to say, okay, how far did we go up and down to get from L to M? And it doesn't matter if it's positive or negative because the sign has already been dealt with. So that would be 6. Then we're going to look left to right, and we're going to say, okay, left to right, how far have I moved? Because that is my run, because we're doing rise over run. That's 1. So segment LM has a slope of -6. Okay, let's try another one. Let's look at KJ, because if KJ is parallel to LM, then that should have the same slope. So again, we're going to look at the overall shape. Well, it's going down to the right, so that's going to be a negative shape. Okay, now we don't care about positives or negatives. All I need now is the rise and the run because I've already figured out the slope is negative based off the shape. Then we check our rise, so we figure out total, how far up and down did I move? 1, 2, 3, 4, 5, 6. Okay. And then lastly, we're going to look left to right, see how far we have run 1 unit. So that one's also -6. So far, it's looking pretty good. Okay, now let's do the top. Top is KL. I want you to look at it and try to think what that slope should be if it's positive or negative. That is a positive slope. It's going up to the right. That is the way you want your bank account to look. So KL has a positive slope. Then I want to look at the rise. The rise is 2. I'm just counting that in blocks. And then we want to look at the run. So how far left and right did this move? 1, 2, 3, 4, 5, 6. It is a good idea to reduce that just because the slope on the other side might also need reduced. And so if we reduce them both, they will match, hopefully. And then we can do the slope on JM. So again, JM has a positive slope. It's going up to the right. That's the way you want your bank account to look. The rise, if we compare the vertical distance between those two, would be 2. And the run, if we compare the horizontal distance between those two, would be 6. So again, it reduces to positive 1/3. Therefore, the conclusion is that JKLM is a parallelogram because opposite sides are parallel. Now, here's the problem with G. 1, the picture doesn't look like a parallelogram, and you can't really tell that to start, but you will see in a second that it's clearly not a parallelogram. I'm going to adjust this problem in the future, but I do still want us to prove that it's not a parallelogram. So it says, given the coordinate of quadrilateral ABCD, prove whether or not the figure is a parallelogram. So as I go through and I start graphing this one, okay, what do I have going on? Well, -3 is A. Okay? Then I have 2, 5, which is the location of point B. I have 5, 2, which is the location of point C. And I have 0, 0, which is the location of point D. So yes, what are you saying? Miss Colbank, there's no way that this is a parallelogram. And you know what? You're right, but we're told to prove it. Okay? I can look at that and know that's a parallelogram. Absolutely. We're proving it. The other problem with this is typically the way that we order letters, you want to be able to work your way around the parallelogram. And this is another issue because if you go around the parallelogram, it is not called ABCD. It is instead called ACBD. Okay, that's totally valid, but that is another issue with this problem, which is why I'm changing it in the future. Let's go ahead, though, and prove, and we can do this quickly, that this is not a parallelogram. All we have to do is show that 2 sides are not parallel, because to have a parallelogram, all 4 sides must be parallel, and so even if 2 of them are not parallel, that's enough. So first, I'm going to find the slope between B and C. It's negative because of the overall shape. The rise is 3, the run is 3, and then we can reduce it to -1. So the slope of BC is -1. If this was a parallelogram, the opposite side, AD, would also have to be -1. Let's check it out. The slope of AD is positive overall, so that's already different. There's still a rise of 3 and a run of 3, so it reduces to +1. But again, these must match if that was a parallelogram. So we can say, okay, definitively, ABCD is not a parallelogram because AD is not parallel to BC. And that would be enough of a reason. I'm realizing that's hard to read. There we go, because AD is not parallel to BC. So those are your notes. That is all I need you to worry about notes-wise. Hopefully you have it completely filled out. If not, go back and look. You can either work on the homework, and please remember that a lot of the homework has consecutive angles versus opposite angles, so pay special attention to that. Add those two angles equal to 180 degrees if you see an example like that. I believe you also have maybe a Delta Math assignment. I honestly can't remember. So if you want to do the digital assignment, that is fine as well. Please be good for the sub. Let me know if you guys need anything, and I will see you on Friday.